Okay, 2.1 probability experiments. So we're going to go over a couple definitions right now. Oh, probability. This is a measure of the likelihood that a specific event will occur. Okay, this can be theoretical or experimental, and we are going to take a look at that between today's lesson and tomorrow's lesson. So, for example, what is the probability when two dice are rolled, both will show ones? Okay, and what is the probability that when a coin is tossed, it will show heads? So just two quick examples. Okay, the probability is always going to be a number between 0 and 1. 0 meaning there's a 0% probability that's ever going to happen, right? So we can say that this event is certain not to happen. We're certain of it. Okay, and 1 means 100% no matter what is going to happen. So we can say this event is certain to happen. Again, that certain word. Okay, and if the result is multiplied by 100, because what this is going to be presented as is 0 decimal and usually 2 digits. What we can do is those 2 digits, when multiplied by 100, that is going to give us a percent. So it's going to be those 2 digits and then a percent sign. Okay, but probability can be expressed as a fraction, a decimal, and a percent. Okay, they're interchangeable. Okay, outcome. An outcome is the result or possible result of an experiment. We say possible result because we could be talking about an experiment, not actually doing it, so it's the possible result. Also, a result may not ever happen. Like you may roll a die 5 times and never roll a 3. So, but 3 is definitely possible as it's a possible outcome. Okay, even if it doesn't happen. Event. An event is a set of outcomes with the same result. Trial. A trial is one round of an experiment. So, for example, rolling a die once, flipping a coin twice, right? So, rolling a die once could be one trial. You could also have flipping a coin twice. So you could be saying like, okay, am I going to get tails and tails or tails and then heads? Heads and then heads or heads and then tails, right? But this combination of what we get for the first outcome and what we get for the second outcome would be still one trial because it depends on what we're actually talking about. In this case, we were talking about like flipping a coin twice. Twice would be one trial. Okay, now let's talk about experimental probability versus theoretical probability. Okay, so an experiment conducted by repeating a set number of times and recording the results. Okay, this is actually when you do an experiment. It's not talking about what could be the outcomes. It's saying do the experiment and record the results. What actually happened in real life. Okay, the results may or can be used to estimate the probability of events. So what we would do is we would calculate the experimental probability of like the probability of and then whatever the desired outcome is. Okay, how many successful trials did we have? AKA, how many desired outcomes occurred? And then we would divide that by the total number of trials. Okay, theoretical probability is similar to experimental probability, except for we're not actually doing the experiment. What we're doing is we're looking at the likelihood that an event is going to occur without actually performing the experiments. Okay, theoretical probability measures possible outcomes. It would be in a very, very fair, perfect world, this would theoretically happen. Okay, and this is calculated using the probability of, again, desired outcomes. So like what we're going after, maybe rolling a 2 on a die, right? How many times could we possibly roll a 2? Well, like, on the sides of a die, it'd be 1, 2, 3, 4, 5, 6. So there's only one chance of rolling a 2 out of 6 different numbers, right? And we don't have to roll it to prove that. Like, I don't have to pick up that die and roll it 600 times to prove that the theoretical probability is 1 out of 6. Theoretical probability is just looking at actual outcomes, okay, in a perfect world. Okay, now we can write probability, and you'll see me write it like this: the probability of, and then whatever event or whatever desired outcome I want. And it's going to be the number of successful trials over the total number of trials. For example, the probability that I roll a 1 out of 6. Example 1, performing an experiment. So a 6-sided die is rolled 20 times, and this chart below shows the outcomes. Okay, complete the frequency column in the chart and create a frequency graph below. So the number rolled on the die, 1, 2, 3, 4, 5, 6. Okay. Usually when you do an experiment, you're going to tally because it's quick. So we have to count these tallies. So this would be 2. So the number 1 appeared twice. The number 2 appeared 3 times. The number 3 appeared 3 times. The number 4 appeared 1, 2, 3, 4, 5. So these are grouped together as 5. I couldn't put the line through it, so they're just grouped together. And then 6. Okay, the number 5 appeared 4 times, and the number 6 appeared twice. So let's call this outcome on a die. Okay, the number rolled, well, obviously it's not going to be 7 or 8. It's just going to be 1 to 6. And then we're going to do the frequency up the side. So the number 1 was rolled twice. So let's go over number 1. And we're going to draw a frequency graph. Okay, bar graph. It's going to look like a histogram because the bar is going to touch, and that's totally fine. Okay, the number 2 is rolled 3 times. So this is going to go up to 3. The number 3 is rolled 3 times, so also here. Number 4 is rolled 6 times, so we're going to go all the way up. Okay. The number 5 is rolled 4 times. And then the number 6 is rolled 2 times. And I'm going to shade those in. Okay, C, find the experimental probability of rolling a 6. Express your answers as a fraction in lowest terms, as a decimal, and as a percent. Okay, so when we talk about experimental probability, we talk about the outcomes that we got from the experiment. So rolling a 6 would be 2. And this question does tell us that a 6-sided die is rolled 20 times. I always just check this just to make sure that the math adds up. So if we add these up, so 6 and 4 is 10. Then we have 2, 3, 4, 5. 2 and 3 is 5. 2 and 3 is 5. So yes, this is a total of 20. So if we think about rolling a 6, the probability of rolling a 6 is 2 out of 20. Okay, this is the fraction. Let's express this in lowest terms. What does both the 2 and the 20 divide by? Well, they both divide by 2, and we get 1 over 10. So what this means is that experimentally, 1 out of every 10 rolls, we're actually rolling a 6. Okay? In regards to the decimal, if we actually did 1 divided by 10 as a decimal, we're going to get 0.1. Okay. I also like to see this as 0.10. And the reason is because when we express this as a percent, so percent, we're going to take 0.10 multiplied by 100. Our percentage is going to be the 2 numbers after the decimal. Okay, 10% of the time. So we have fraction, decimal, and a percent. All right. Find the experimental probability of not rolling a 6. Okay, so the probability of not a 6 is actually just going to be the probability of rolling a 1, a 2, a 3, a 4, or a 5. And then what we'll do is we'll relate it to the probability of rolling a 6. So the probability of rolling a 1 is 2 out of 20. The probability of rolling a 2 is 3. Probability of rolling a 3 is 3. So plus 3 out of 20 plus 3 out of 20. The probability of rolling a 4 is 6. And the probability of rolling a 5 is 4. So 6 out of 20 plus 4 out of 20. Okay. Because we're adding fractions with the same denominator, we keep that denominator and we add 6 and 4 is 10, 3 and 3 is 6, 7, 8. This is going to be 18 out of 20. So now let's compare. Okay, by the way, 18 over 20, we could divide both of these by 2, and we get 9 over 10. So let's use that one. Let's use 9 over 10, and let's compare it to 1 over 10. Okay, how is it related to the probability of rolling a 6? Okay, essentially what's going to happen is like the probability of not a 6 is going to be all of the leftover probability of not rolling a 6. So let's go, probability of not 6 will be all of the, and we can call it like leftover probability of the probability of rolling a 6. Okay, and if you think about it, 1 over 10 and 9 over 10 gives you 10 over 10. And 10 over 10 is 100%. And what that 100% does is this 100% accounts for all outcomes. Okay, it counts for every single time we rolled that die. Okay, and how would you expect the heights of the bars to relate to each other? Okay, so I'm going to say the more frequent an event occurs, the taller the bar. Okay, and then in turn, less frequent the event occurs, then obviously like the shorter the bar. Example 2, a coin was tossed 50 times. The experimental probability of turning up heads was 2 out of 5. So if you think about it, if you're tossing a coin 50 times, 2 out of 5 times was heads. So if you group together 5 rolls, it'd be like heads, heads, tails, tails, tails. And then another 5 rolls. So this would be 10 rolls. Heads, heads, tails, tails, tails. And then another 5 rolls. Heads, heads, tails, tails, tails. Okay? And you're doing basically 10 of these groupings, right? Because 10 groupings of 5 rolls will be 50 tosses. Okay, so we're looking at like the grand scheme of these 50 tosses. What is going on? Okay, so again, experimental probability, that's what we're focusing on. Okay, if it was theoretical probability, it'd be 50-50, right? It'd be half the time it's heads, half the time it's tails, because there's two outcomes. But it's not in this case. So explain what the probability means in this experiment. Okay, so the probability that heads turned up 2 out of 5 times means out of every 5 tosses, heads was tossed 2 times. That's what that means. And that's why I was talking about the groupings. Out of every 5 tosses, right, the groupings of 5, heads was tossed 2 times. Okay, B, how many times did the coin turn up heads in the experiment? So that's in the entire experiment. How many times? So here's the thing. The coin turned up heads 2 out of 5 times. So we want to know, what is that out of 50? So what number can we multiply 2 and can we multiply 5 by so that the 5 times this number equals 50? So essentially what we're doing, we're saying, okay, if we have 50 rolls and there's 5 rolls per bunch, how many is that? Well, that's 10. That's a side. Okay, so 2 times 10 and 5 times 10. It's going to give us 20 rolls out of 50 are going to turn up heads. So in other words, how many times? So we can say heads turned up 20 times. So what this means is that, so if we rolled it 50 times and 20 of them were heads, well, how many were tails? Well, all the leftovers were tails. So 30. 30 tosses were tails. Right? Because we do the total minus what we already accounted for, which was the heads. Right? So we can say like total minus heads will give us how many tails. So now for D, oh, it should be C. What is the experimental probability of the coin turning up heads? So the probability of heads is going to be this fraction, right? 20 out of 50. In other words, 2 out of 5. And we were actually given this right here. The experimental probability of heads was 2 out of 5. Okay, and now if we consider tails, well, the probability of tails is going to be the 30 out of the 50, which is 3 out of 5. Okay, and all I did to get 3 out of 5 was divide the numerator and the denominator by 10. Example 3, the following graph displays the frequencies in the number of females in families who have 6 children. Answer the following questions. How many trials were performed altogether? So what I'm going to do is I'm going to go over all of the outcomes, 0, 1, 2, 3, 4, 5, 6, and I'm going to write on top the number of females that they have as like pretty much as kids, right? Out of their kids. So one family has 0 girls. Imagine having 6 boys. Okay, 0 families have 1 girl. Okay, 2 families have oh, sorry, 4 families have 2 girls. 6 families have 3 girls, and then 3 families have 4 girls, 3 families have 5 girls, and then none of the families have like all girls. Okay, so how many trials were performed altogether? So if we added all of these up, all of the outcomes up, okay, so we can write total outcomes. 1 plus 0 plus 4 plus 6 plus 3 plus 3 plus 0. We get, that's 10, 3 and 3, 6, 7. I get 17. So they asked 17 different families, how many girls do you have? All right, out of your 6 kids, how many are girls, how many are boys? Okay. B, what is the experimental probability of having 2 females in a family of 6 children? So, probability of 2 females is, well, number of females 2, right? So there's 4 families that have 2 girls. So it's 4 out of a total of 17 families. C, according to this experiment, what is the average number of females in a family with 6 children, and how can you tell? Okay, so taking a look at the bar graph, it's probably going to be like around 3, right? A couple are lower and a couple are higher, and then 2 are right on the 3. But let's actually numerically calculate. So we have a total of 17 families. Okay, so there's a total of 17 families. Now let's actually count how many kids, how many females are in total. So for 0 females, there's going to be 0 females there. So we're not going to count that one. For 1 family, there's 0 females. Let's not count this. For 1 female, there's 0 families. Okay, so for 2 families, there are 4 females. So far we have 4 plus 4 females. So there are 3 females in 6 families. Sorry, I did this backwards. There are 2 females in 4 of the families. So 2 plus 2 plus 2 plus 2. That will give us 8 females so far. There are 3 females 6 times for the frequency. So there's 3 females, 3 females, 3 females, 3, 3, 3. So C, what is the probability that the families have 2 or 3 females? So let's take a look at 2 or 3 females. We have 4 families and 6 families. So 4 out of 17 families have 2 girl kids, and 6 out of 17 families have 3 like female or girl children. So a total of 10 out of 17 families have either 2 or 3. Okay, and we add these because we're talking about like different scenarios here. So we're saying, okay, there's 2 scenarios. What's probability of this or this happening? Okay, so we're adding them. Now, what's the probability that a family has less than 4 female children? So less than 4, because it's not 4 or less, it's less than 4. So that means 3, 2, 1, or 0. So how many families have 3 girls? 6. How many families have 2 girls? 4. How many families have 1 girl? 0. How many families have 0 girls? 1. Okay, so this is going to give us a total of 11 out of 17 families have less than 4 female children.